4 minutes. That is how long Mission Control will sit in total silence tonight, while 4 human beings ride a fireball through the atmosphere at 40,000 kilometers per hour. No telemetry, no voice contact, no way to send a single command. And here's the part nobody is saying loud enough. The heat shield protecting those astronauts is the same design that shattered in over 100 locations during its only test flight. NASA saw the damage, studied it, documented it, and then decided to put people behind it anyway. Their own risk estimates range from 1 in 50 to a coin flip. I am going to walk you through exactly why they made that decision, what actually broke, and why the next 4 minutes could determine whether humanity goes back to the moon or gives up for another 50 years. If you are new here, hit like and subscribe, because tonight is not the end of this story. It is the beginning. Whether that heat shield holds or whether it does not, what happens next reshapes human spaceflight for decades. And this channel will be here for every piece of it, every investigation, every mission update, every engineering detail that everyone else skips over because it does not fit in a headline. We break it all down so it actually makes sense. You will want to be here for what comes after those 4 minutes of silence. Now, let us get into it. Right now, somewhere above the Pacific Ocean, 4 human beings are falling toward Earth at 32 times the speed of sound. And in about 6 minutes, every single person in Mission Control is going to lose contact with them completely. This is not a malfunction. This is the plan. The Orion capsule carrying the Artemis II crew is approaching what engineers call the entry interface, a boundary roughly 122 kilometers above the surface where the atmosphere stops being a suggestion and starts being a wall. At approximately 40,000 kilometers per hour, Orion is moving faster than any crewed vehicle in history. Faster than Apollo, faster than the shuttle, faster than anything with a heartbeat inside it has ever gone. And at that speed, the air in front of the capsule does not move out of the way. It compresses, it heats, it breaks apart at the molecular level, stripping electrons from atoms and creating a superheated envelope of ionized gas, plasma, that wraps around the vehicle like a burning cocoon. That plasma is so electrically dense that it blocks every radio frequency we use. Voice communications, telemetry, GPS, tracking signals, all of it, gone. For roughly 4 minutes, Orion becomes a ghost. Mission Control sees nothing, hears nothing, cannot send a single command. The screens on the consoles at Johnson Space Center will show the last known trajectory, and then they will stop updating. And everyone in that room will sit there, silent, staring at a number that says how many seconds remain until the signal should come back. Should. Now here's the part that keeps people up at night. That heat shield on the bottom of Orion, the one thing standing between the crew and temperatures exceeding 2,000 degrees Celsius, is the same design that was tested on the uncrewed Artemis I mission. And when they pulled that capsule out of the ocean and started inspecting it, they found damage in over 100 locations across the shield. Cracking, material loss. Pieces of the ablative coating had broken away in chunks that were never supposed to come off. Not like that. Not in those patterns. Not in those quantities. And NASA decided to fly the next mission with the same shield design, with people on board. The agency's own internal risk estimates for loss of crew during re-entry range from 1 in 50 to 1 in 2. That is not a typo. One end of that range means a coin flip, and unlike almost every other phase of the mission, there is no abort option during re-entry. Once Orion hits that atmosphere, the crew is committed. There is no engine burn that pulls them back up. There is no escape system that fires them free. They ride it down, or they do not make it down at all. So tonight, the most dangerous moment in human spaceflight since the Columbia disaster comes down to this. Not whether we can get 4 astronauts to the moon, because honestly, that is the straightforward part. The real question, the one that every engineer and flight director and physicist is quietly turning over in their mind, is whether we can get them home. And what NASA discovered after Artemis I is exactly why this moment exists at all. When the Artemis I capsule splashed down in the Pacific Ocean on December 11th, 2022, the mission was declared a success. And in most ways, it was. Orion flew to the moon, looped around it, came back, and landed within a few kilometers of the target zone. The flight computers worked. The service module worked. The parachutes deployed. From a systems perspective, it was nearly flawless. But when recovery teams hauled the capsule onto the deck of the USS Portland and engineers got their first good look at the heat shield, the celebration got a lot quieter. Across the surface of the ablative material, they found cracking and char loss in more than 100 distinct locations. Some of it was expected. Ablative shields are designed to erode, and that is the whole point. They burn away in a controlled fashion to carry heat with them. But this was not controlled. Pieces had separated in ways the thermal models did not predict. In some areas, material had come off in irregular chunks rather than the smooth, even recession the simulation showed. The pattern did not match any pre-flight prediction. And for a system that is supposed to behave with extreme precision during the most violent phase of the entire mission, we did not expect that, is a deeply uncomfortable sentence. Now, the logical response might seem obvious. Fix it. Redesign the shield. Replace it with something that does not crack apart when it encounters real re-entry conditions. But that is where the math gets complicated, and not just the engineering math. The political math, the budget math, the schedule math. Artemis II had already been delayed multiple times. The original target was late 2024. That slipped to 2025. Then, 2026. Every delay costs hundreds of millions of dollars, strains relationships with international partners, and gives critics of the program more ammunition to argue that the whole thing should be scrapped in favor of something cheaper or faster. There was also a less obvious, but equally important engineering argument. If you redesign the heat shield, you are introducing a new, untested variable. The current shield, damaged as it was, had at least flown. Its failure modes had been observed, studied, and to some extent understood. A brand new design would bring its own unknowns. You would be trading a known risk for an unknown one. And in aerospace, unknown risks have a nasty habit of being worse than the ones you can see coming. So NASA made a decision. Fly as is. Keep the same Avcoat heat shield material. Keep the same block construction, but change the way the capsule comes home. Instead of the skip re-entry profile used on Artemis I, Artemis II would fly a direct steeper descent. The theory was straightforward enough. If the skip maneuver caused the damage, then removing the skip removes the damage mechanism. You do not fix the shield. You fix the trajectory. Jared Isaacman, the mission commander, was briefed on the risk. The crew accepted it. That is how human spaceflight works, at least on paper. Astronauts are test pilots. They understand that some level of danger is baked into the job. But there is a difference between accepting risk and accepting uncertainty, and this situation has a lot more of the latter than most people realize. Because the truth is, NASA is not entirely sure why the shield behaved the way it did. They have theories. They have models. They have ground tests that partially replicate the conditions. But partially is doing a lot of work in that sentence. And here is where it starts to rhyme with history in a way that makes engineers uncomfortable. Before the Columbia disaster in 2003, NASA knew that foam was striking the shuttle's thermal tiles during launch. It had happened on multiple flights. The damage was observed, documented, discussed, and each time it happened without catastrophic failure, the acceptable risk window quietly widened. Engineers raised concerns. Management weighed schedules and budgets. The foam strikes became in family, meaning they fell within the range of previously survived events. Until the one that did not. Nobody is saying Artemis is Columbia. The situations are different in important ways. But the pattern, known damage, schedule pressure, a decision to continue rather than stop, that pattern has a name in aerospace safety culture. It is called normalization of deviance. And it is the single most common thread connecting every major spaceflight disaster in history. To understand why NASA accepted this level of risk, though, you first have to understand what actually went wrong with the heat shield. Because the failure was not simple. It was not a case of the material being too weak or the heat being too intense. It was something stranger, something that requires a specific sequence of events to occur, a sequence that the original design never accounted for. The way Orion came home during Artemis I was not the way Apollo came home. And that distinction matters more than almost anyone outside of aerospace engineering realizes. During the Apollo missions, the capsule hit the atmosphere on a direct path. It plunged in, decelerated hard, endured a continuous blast of thermal energy, and deployed parachutes once it slowed down enough. It was brutal, but it was straightforward. One entry, one sustained heating event, one ride down. Artemis I used a different technique called a skip reentry. Think of it like skipping a stone on a lake. Orion dipped into the upper atmosphere, used that friction to bleed off some speed and generate lift, then actually climbed back out of the atmosphere briefly before plunging in again for the final descent. The purpose was practical. Skipping allows the capsule to extend its range, meaning it can reach landing zones that are farther from the initial entry point. It also spreads the thermal load across two separate heating pulses instead of one, which, on paper, reduces the peak temperature the shield has to endure at any single moment. Engineers figured this would be gentler. In some ways, it was. The peak surface temperatures during each dip were lower than what a direct entry would produce. But something else happened that nobody fully anticipated. During the first atmospheric pass, the outer surface of the heat shield heated up enormously, as expected. The ablative material began to char and erode, doing its job. But when Orion skipped back out of the atmosphere, that outer surface suddenly cooled. The problem was that the interior of the shield material was still hot. The char layer had insulated the deeper layers, trapping thermal energy inside. And when hot material suddenly gets capped by a cooling outer surface, the gases produced by pyrolysis, the chemical decomposition happening within the ablative material, have nowhere to go. They get trapped. Pressure builds. Little pockets form inside the structure, like bubbles in bread dough, except these bubbles are full of superheated gas pushing outward against a layer that has just become rigid and brittle from cooling. Then Orion hit the atmosphere a second time. The outer surface reheated rapidly. The thermal stresses shifted again, and those internal pressure pockets released violently. Material fractured and broke away in chunks. Not because the heat was too extreme, but because the specific pattern of heating, cooling, and reheating created a failure mechanism that the ground tests had never reproduced. The skip itself was the trigger. So NASA's logic for Artemis II is, in a certain sense, straightforward. If the skip caused the cracking, eliminate the skip. Artemis II will fly a direct re-entry, more like what Apollo did. One plunge, no skip, no cooling pause, no trapped gas pockets. Problem solved. Except it might not be that simple. A direct re-entry means higher peak temperatures sustained over a shorter window. Instead of two moderate heating pulses, the shield takes one intense, continuous blast. The total energy load might be comparable, but the delivery is completely different. And materials do not always care about total energy. They care about how fast and how concentrated that energy arrives. a piece of wood can survive an hour near a campfire. Put it in a blast furnace for 30 seconds, and it is gone. Same total energy, completely different outcome. There is also the question of structural versus thermal stress. During Artemis I, the shield proved it could handle the thermal job. The cabin behind it stayed at manageable temperatures, close to room temperature in fact. Nobody inside would have been burned, but the structural behavior, how the material held together physically, that is a different engineering problem entirely. You can have a shield that blocks every joule of heat from reaching the crew and still fails catastrophically if pieces of it break off in a way that exposes underlying structure or shifts the aerodynamic balance of the capsule. And this is the part that is hard to test on the ground. No facility on Earth can perfectly replicate the combined conditions of orbital reentry. You can simulate the heat in an arc jet facility. You can simulate the vibration on a shake table. You can simulate the pressure in a wind tunnel, but you cannot do all of it simultaneously at the exact speed, density, and duration that the actual reentry produces. Every ground test is an approximation. Some are very good approximations. None of them are the real thing. So Artemis II is flying a re-entry profile that has never been tested with this heat shield, on a vehicle that has never carried crew, using a trajectory that was specifically designed to avoid one failure mode, but that introduces conditions the material has never actually experienced in flight. The old failure was understood, more or less. The new profile is, by definition, uncharted, and the heat shield did not fail the way anyone expected the first time. It failed in a way that should not have happened according to every model they had, which raises a question that no amount of ground testing can fully answer. What else might happen that the models do not predict? Here is a number that should bother you. NASA's estimated probability of loss of crew during the Artemis II re-entry ranges from 1 in 50 to 1 in 2. That is not a tight range. That is an enormous spread. 1 in 50 means roughly a 2% chance of catastrophic failure. 1 in 2 means 50%. The distance between those two numbers represents a chasm of uncertainty that would be unacceptable in almost any other context involving human life. NASA's general threshold for acceptable risk on crewed missions is around 1 in 300 for the overall mission and roughly 1 in 30 for any single phase. Even the optimistic end of the re-entry estimate, 1 in 50, exceeds that single phase threshold. The pessimistic end is not even in the same universe, and the reason the range is so wide is not because the engineers are being sloppy. It is because the problem genuinely resists precise calculation. Modeling heat shield behavior during re-entry requires simulating an absurd number of variables simultaneously. Surface temperature gradients, internal gas generation rates, material recession profiles, aerodynamic shear forces, vibrational loads, structural bonding integrity, atmospheric density fluctuations, angle of attack variations, and the interactions between all of these happening in real time at hypersonic speed. Each variable carries its own margin of error. When you stack uncertain estimates on top of uncertain estimates across dozens of parameters, the output range balloons. The model does not converge on a clean number. It produces a spread that reflects how much the engineers do not know. And this is where a concept that rarely makes it into press conferences becomes important. There is a difference between risk and uncertainty. Risk is when you know the odds. You roll a die, you know there is a 1 in 6 chance of any given face. Uncertainty is when you do not know the odds because the system is too complex, or too novel, or too poorly understood to assign reliable probabilities. The Artemis II re-entry sits firmly in the second category. The engineers are not saying, we think there is a 1 in X chance of failure. They are saying, we think the chance of failure falls somewhere in this enormous range, and we are not sure where. This is sometimes called epistemic uncertainty, a term that basically means we are uncertain about our own uncertainty. We do not just lack the answer, we lack confidence in the tools we are using to look for the answer. The models that generate these risk estimates are built on assumptions. Some of those assumptions have been validated by ground tests. Some have been validated by the single data point of Artemis I. And some have not been validated at all, because the conditions of Artemis II are, by design, different from anything that has been tested before. Now, to be fair, this is not new. Apollo astronauts flew with comparable or even greater levels of uncertainty. The difference was partly cultural. In the 1960s, the risk tolerance was simply higher, both among the astronauts and the public. People accepted that going to the moon might kill you because the Cold War framed it as a national imperative. The astronauts were military test pilots accustomed to routinely climbing into machines that had a meaningful chance of not bringing them back. And the public did not have real-time access to internal risk assessments, engineering memos, or failure probability ranges published on the internet. The uncertainty existed. It just was not visible in the same way. Today, the situation is reversed. The public expects precision. People have been conditioned by decades of commercial aviation, where the fatal accident rate is measured in fractions per million flights, to believe that engineered systems can be made essentially fail-safe. When NASA publishes a risk range that includes 1 and 2, even as a worst-case bound, it triggers a visceral response that the Apollo-era estimates never provoked, simply because nobody was reading them in real time on social media. There is also an internal dimension to this that rarely gets discussed publicly. Not every engineer at NASA agrees that the risk is acceptable. These disagreements are not dramatic shouting matches or leaked memos, at least not yet. They are quieter. They show up in the margins of review documents, in the caveats appended to analysis reports, in the questions asked during technical meetings that receive answers beginning with, "Our current best estimate suggests." That phrasing, "current best estimate," is engineering code for, "We think this is right, but we would not bet our own lives on it with total confidence." And the uncertainty starts with the material itself, because the AvCoat heat shield is not a simple slab of protective coating. It is an engineered system of 186 individual blocks, bonded together in a pattern that has never existed on any previous spacecraft, and the way those blocks behave under the specific conditions of this re-entry is genuinely unknown. Every heat shield that has ever brought a human being home from space works on the same basic principle. You sacrifice the shield to save the crew. The technical term is ablation. The material on the outside of the capsule is designed to absorb enormous quantities of thermal energy, undergo chemical decomposition, and then carry that energy away as it erodes. The heat does not get through because the shield material takes the hit and leaves, carrying the heat with it like a bouncer escorting trouble out of a building. What remains behind stays cool enough to protect the structure underneath. It is destruction by design. Controlled, predictable destruction. AvCoat is the specific ablative material on Orion's heat shield, and it has history. A version of it was used on the Apollo capsules in the 1960s and 70s. It is made from silica fibers in a honeycomb structure, filled with an epoxy resin that chars and decomposes when exposed to extreme heat. As the outer layer chars, it forms an insulating crust. As that crust erodes, it pulls heat away from the surface. Meanwhile, gases produced by the decomposition of deeper layers percolate outward through the char, creating a thin boundary layer that further insulates the surface. It is an elegant, multi-layered process, and when it works correctly, it is remarkably effective. Artemis I proved that the thermal protection part works. The cabin behind the heat shield stayed at manageable temperatures throughout re-entry. If there had been astronauts on board, they would not have been harmed by heat penetration. The shield did its primary thermal job. But here's the thing about ablative shields that most people do not appreciate. Thermal protection is only half the requirement. The other half is structural integrity. The shield does not just have to block heat. It has to block heat while maintaining its physical shape and mechanical cohesion under conditions that include hypersonic aerodynamic forces, severe vibration, massive pressure differentials, and thermal gradients that can vary by hundreds of degrees across a few centimeters. If chunks of the shield break away unpredictably, even if the remaining material continues to block heat, you now have an asymmetric surface. The aerodynamic profile changes. Drag becomes uneven. The capsule can start to wobble or shift attitude in ways the guidance system was not designed to handle. In the worst case, exposed underlying structure gets hit with temperatures it was never meant to withstand. So the paradox of Artemis I is this. The heat shield succeeded at its thermal mission and failed at its structural mission simultaneously. The crew would have survived the heat. But the unpredictable loss of material introduces a variable that makes the next flight harder to model, not easier. Because now you have to predict not just how the material erodes thermally, but when and where it might fracture mechanically. And those are two very different problems governed by two very different sets of physics. The predictability is everything. A shield that erodes a little more than expected is manageable, as long as it does so smoothly and evenly. A shield that sheds chunks at random is a different kind of problem entirely, and the root of that unpredictability may not be the material itself. It may be the way the shield is constructed. The Apollo heat shield was built as a single, continuous structure. The AVCoat material was applied in a honeycomb matrix of roughly 320,000 small cells, each one filled individually with the ablative compound. This produced a remarkably uniform surface. Every point on the shield had essentially the same composition, the same density, the same structural characteristics. There were no joints, no seams, no boundaries between large sections. It was, for practical purposes, one piece. Orion's heat shield is not built that way. The modern AVCoat shield is manufactured as 186 individual blocks. Each block is prefabricated separately and then bonded to the underlying titanium skeleton of the heat shield structure. The reason for this change is practical. Filling 320,000 honeycomb cells one at a time is extraordinarily labor-intensive and time-consuming. Manufacturing large pre-made blocks and attaching them is faster, cheaper, and more compatible with modern production methods. From a manufacturing and schedule perspective, it makes complete sense. From a structural perspective, it introduces complications that did not exist before. Every boundary between two blocks is a seam. Every seam is a joint where two separately manufactured pieces of material meet, held together by an adhesive bond, rather than by continuous material structure. Under normal conditions, these bonds are strong. Under re-entry conditions, they become potential weak points, because when the shield heats up, the material expands. Different blocks may expand at slightly different rates depending on minor variations in composition, density, or orientation. The seams between them experience shear stress, tension, compression, and thermal cycling that the interior of a continuous structure would not. These are the points where cracks are most likely to initiate. These are the locations where fracture pathways can propagate. And these are the areas that ground testing has the hardest time replicating accurately, because the exact bonding conditions, curing process, and micro-scale variations of a flight article are never perfectly reproduced in a test sample. Now, I should be clear that this is partly speculative territory. NASA has not publicly confirmed that the block seams were the primary failure initiation sites on Artemis I. The investigation identified the skip re-entry thermal cycling as the main driver of the charring and material loss. But multiple independent analysts and former NASA engineers have pointed out that the block construction creates inherent stress concentration points that would not exist in a monolithic design. And stress concentration points are where failures begin. Always. in every material, in every structure, under every loading condition. That is not speculation. That is materials science. The engineering debate here is a classic trade-off between manufacturing efficiency and structural performance. The block design makes the shield feasible to produce on a realistic schedule and budget. The monolithic design would be structurally superior, but might take years longer to manufacture and cost significantly more. In a program that has already blown past its original schedule and budget by wide margins, that trade-off is not purely technical. It is political. It is financial. And those pressures have a way of tilting decisions in directions that the physics might not fully support. The real question, though, is not whether the blocks are a problem in theory. It is whether the specific failure observed on Artemis one began at the seams. Because if it did, then changing the re-entry profile does not actually address the root cause. It addresses a symptom. The thermal cycling may have triggered the fractures, but the structural vulnerability that allowed the fractures to propagate might still be there, waiting for a different trigger. And the failure that actually occurred inside the material was stranger than a simple crack at a seam. Picture a piece of avcoat about a meter square, bonded to the heat shield, plunging into the atmosphere at hypersonic speed. The outer face hits temperatures exceeding 2,000 degrees Celsius. The ablative process begins immediately. The surface chars, darkens, starts to erode. Gases generated by pyrolysis, the thermal decomposition of the resin component, begin percolating outward through the porous char layer. So far, everything is going according to plan. This is exactly what the material is supposed to do. But during the Artemis I skip re-entry, something additional happened. After the first atmospheric pass, Orion climbed back above the sensible atmosphere. The outer surface, which had been subjected to ferocious heating, suddenly found itself in the cold vacuum of space. Radiative cooling began pulling heat out of the charred surface rapidly. Within minutes, the outermost layer had cooled significantly and begun to stiffen and contract. The problem was underneath. The interior of the shield was still hot. The char layer that had formed on the outside was actually doing too good a job as an insulator, trapping thermal energy in the mid-depth regions of the material. This is where pyrolysis was still active. The resin was still decomposing. Gases were still being generated. But now, the escape route that those gases would normally take, percolating outward through a hot, porous char layer, was partially sealed. The cooled outer crust had become denser, less permeable, essentially forming a cap over a pressure cooker. Gas pressure built up in the interior of the material. Small voids formed, pockets of trapped gas pushing outward against a layer that was becoming increasingly rigid and brittle. And the material sat like that, pressurized and stressed, as Orion coasted through the skip phase. Then came the second atmospheric entry. The outer surface reheated rapidly. The thermal gradients reversed. The rigid outer crust that had been holding the gas in was now being heated again from the outside, while the internal pressure was still pushing from the inside. The competing forces cracked the material. Sections fractured and broke away, not in a smooth erosion pattern, but in chunks. Irregular, unpredictable chunks that scattered into the plasma wake behind the capsule. This is the key insight. The failure was not caused by the heat being too intense. It was caused by a specific sequence: heating, cooling, internal gas generation, pressure trapping, reheating, and fracture. Remove any step in that sequence, and the failure does not occur, at least not in the same way. NASA's conclusion was that the skip re-entry was the critical enabler because it created the cooling pause that allowed pressure to build. Direct re-entry, with no pause, should eliminate that specific mechanism. Should. That word is carrying a tremendous amount of weight. Because while the skip sequence has been identified as the trigger, the underlying material behavior that allowed the pressure buildup is not a quirk of the skip profile. It is a property of the material under certain thermal conditions. The pyrolysis gases are always generated during heating. The char layer always becomes less permeable as it densifies. The question is whether continuous heating produces a fast enough erosion rate to keep the gas pathways open, preventing the pressure buildup that the cooling pause created. NASA's models say yes. The continuous erosion during direct reentry should maintain porosity and allow gases to escape without accumulating. But these are the same models that did not predict the Artemis I failure in the first place. They have been updated, refined, tuned to match the observed data. And updated models that are tuned to match one data point are very good at explaining that one data point. They are not necessarily good at predicting what happens under different conditions. This is the uncomfortable position Artemis II occupies. The known failure mode has been addressed. But the underlying material behavior that enabled it has not been changed. The shield is the same. The blocks are the same. The bonding is the same. Only the trajectory is different. And the question of whether that difference is enough is not a question that can be answered with certainty before the actual reentry. Fixing one problem may have shifted the vulnerability somewhere else. Let me describe what happens during a direct re-entry at Orion's speed, because it is not the same as what Apollo experienced, even though the trajectory concept is similar. Orion returns from lunar distance, carrying significantly more energy than the space shuttle ever did. The shuttle re-entered from low Earth orbit at roughly 28,000 kilometers per hour. Orion comes in at about 40,000. That additional 12,000 kilometers per hour represents a massive increase in kinetic energy, roughly doubling the total thermal load. Apollo dealt with similar speeds, but the capsule was smaller, lighter, and the shield was built differently. Orion is the largest crewed re-entry vehicle ever constructed, and its heat shield is the largest ablative shield ever flown. Scale matters. The thermal and structural dynamics of a 5-meter diameter shield are not simply scaled-up versions of a 4-meter one. The stress distributions change. The vibrational modes change. The aerothermal interactions at the edges and in the wake region behave differently. During direct re-entry, the shield experiences continuous, uninterrupted heating for the entire descent through the thermally significant portion of the atmosphere. Peak surface temperatures will likely exceed 2,500 degrees Celsius. The ablation rate will be high and sustained. There is no pause, no cooling period, no opportunity for the material to relax. This addresses the skip-related pressure buildup, but it introduces its own concerns. Continuous high-rate ablation means the shield is eroding faster, consuming more material per second than it would during either phase of a skip entry. If the erosion is uniform, this is fine. The shield was designed with margin. There is more material than the minimum needed. But if the erosion is uneven, and there are reasons to think it might be given the block construction and seam geometry, then you can end up with areas that thin out faster than others. Differential erosion creates an uneven surface. An uneven surface changes the local aerodynamic flow. Changed flow can concentrate heating in areas that are already thin. This is a positive feedback loop, and positive feedback loops in engineering are the things that turn small problems into catastrophic ones very quickly. There is also the question of mechanical loading. A direct re-entry produces higher peak G-forces than a skip entry. The skip spreads deceleration across 2 passes. Direct entry concentrates it into 1. The crew will experience something in the range of 4 to 5 Gs, possibly higher. That is survivable, well within human tolerance. But the heat shield is also experiencing those G-forces. Every one of those 186 blocks is being pushed against the underlying structure by the aerodynamic force of deceleration. At the same time, it is being pulled outward by aerodynamic suction in certain regions, sheared laterally by crossflow, and vibrated by turbulent boundary layer fluctuations, all while the material is actively decomposing and weakening from heat exposure. real reentry is not a single variable problem. It is not just heat. It is not just pressure. It is not just vibration. It is all of them, simultaneously, interacting with each other in ways that are ferociously difficult to model. A piece of material that withstands any one of those loads in isolation might fail under the combination. And the specific combination that Artemis II's direct entry produces has never been experienced by this shield design. Not in flight, not on the ground, nowhere. The concern among some engineers is not that the old failure mode will repeat. That is unlikely, given the removal of the skip. The concern is that a different failure mode will emerge, one that the models do not predict because the models were built to understand the conditions of the previous flight, not the conditions of this one. Every time you change a major parameter in a complex system, you open the door to failure modes that you did not know existed because you never had a reason to look for them. And all of this leads to the moment when no one will be able to see what is happening. Because once Orion enters that plasma sheath, every instrument, every camera, every communication link that connects the crew to the ground goes dark. Whatever happens to the heat shield during those 4 minutes happens in total informational silence. There is a moment during every orbital re-entry that has existed since the very first human spaceflight, and despite more than 6 decades of technological advancement, nobody has figured out how to eliminate it. When a vehicle enters the atmosphere at orbital or superorbital speed, the kinetic energy is so enormous that it does not just heat the air. It tears the air apart at the atomic level. Nitrogen and oxygen molecules are ripped into individual atoms. Those atoms are stripped of their electrons. The gas becomes plasma, a soup of free ions and electrons that behaves very differently from normal air. And one of the ways it behaves differently is that it reflects and absorbs electromagnetic radiation across a wide range of frequencies. This is not a technical limitation that can be solved with a better antenna or a more powerful transmitter. This is physics. The plasma sheath surrounding the vehicle during peak heating has an electron density high enough to block every communication frequency currently used in spacecraft operations. Radio waves, microwave signals, the S-band and Q-band frequencies used for voice and telemetry, all of them get absorbed or reflected by the ionized gas layer. The vehicle might as well be inside a Faraday cage made of fire. The blackout occurs during the period of maximum heating when the shield is under the greatest stress and the crew is most vulnerable. It lasts approximately 4 minutes for a lunar return re-entry, though the exact duration depends on the vehicle's speed, angle, and atmospheric conditions. 4 minutes during which the heat shield is either working or failing. 4 minutes during which the crew is alive or not, and nobody on the ground has any way to determine which. There have been theoretical proposals for getting around this. Electromagnetic windows using magnetic fields to part the plasma. Relay communications through satellites positioned behind the vehicle. Higher frequency signals that might penetrate the sheath. None of these are currently operational on Orion. None were mature enough to implement on this timeline. The blackout exists today for the same reason it existed in 1961 when Yuri Gagarin experienced it. We have not solved the problem because, frankly, we have not needed to. Every previous re-entry has either worked or failed before anyone could do anything about it anyway. The blackout is terrifying, not because it causes problems, but because it hides them. And that is the part that terrifies mission control. It is not the heat. It is not the risk number. It is the silence. 4 minutes of staring at screens that show nothing, knowing that the most critical phase of the most dangerous mission in decades is happening right now, and there is literally nothing anyone can do but wait. This silence has a history, and not all of it ends well. In April of 1970, Apollo 13 hit its re-entry blackout under circumstances that no one in mission control will ever forget. The capsule had been crippled by an oxygen tank explosion days earlier. The heat shield had been exposed to the cold of deep space for far longer than designed. The guidance system had been powered down to conserve electricity and then reactivated with uncertain accuracy. Nobody knew if the shield was intact. Nobody knew if the trajectory was precise. And when the radio signal dropped out at the entry interface, the clock started. The expected blackout duration was about 3 minutes. 3 minutes passed. No signal. 4 minutes. Nothing. 5 minutes. The room was completely still. 6 minutes. 6 minutes of silence from a spacecraft that had been leaking, freezing, and limping its way home with 3 men aboard who had not slept properly in days and were running on adrenaline and recycled air. People in that room later described the experience as the longest minutes of their lives, not because anything was happening, because nothing was happening. No data, no sound, no indication of success or failure. Just screens showing predicted positions on a trajectory that might or might not still be valid. At 6 minutes and 17 seconds, the signal came back. The capsule was intact. The crew was alive. The room erupted. But those extra 3 minutes had aged people visibly. Flight directors who had maintained ironclad composure through the entire crisis later admitted that the blackout was worse than any of it. Worse than the explosion. Worse than the improvised CO2 scrubbers. Worse than the freezing cabin and the dwindling power. Because during all of those events, they could see what was happening. They could think. They could act. During the blackout, they could only wait. And for human beings who are trained to solve problems, who have spent their entire careers being the ones who can always do something, that enforced helplessness is its own kind of torment. Artemis II will be different in some ways. The capsule is not damaged, at least not in any way the crew can detect. The trajectory is being flown as planned, not jury-rigged from a crippled spacecraft. The power systems are nominal. The guidance is precise. But the heat shield carries a question mark that Apollo 13's did not. The Apollo shield was untested under those specific conditions, but was structurally sound. The Artemis shield has been tested under different conditions and shown structural anomalies. The uncertainty is not about systems failing from an emergency. It is about a known vulnerability performing under new conditions. And the mission controllers for Artemis II will be staring at the same silent screens, counting the same seconds, experiencing the same powerlessness, knowing that the worst-case scenario is not dramatic. It is just quiet. The signal simply never comes back. No explosion they can see, no cry for help they can hear. Just an empty frequency and a clock that keeps counting past the moment when the signal should have returned. History shows that when the signal does come back, the relief is indescribable. But history also shows something else. On February 1st, 2003, the Space Shuttle Columbia broke apart during re-entry over Texas and Louisiana at an altitude of roughly 61 kilometers, traveling at approximately 20,000 kilometers per hour. All 7 crew members were killed. The cause was a piece of insulating foam that had separated from the external tank during launch 16 days earlier and struck the leading edge of the left wing, damaging the reinforced carbon-carbon thermal protection panels. During re-entry, superheated plasma penetrated through the damaged site and entered the wing structure. The internal aluminum supports melted. The wing failed. The shuttle lost control and disintegrated. What makes Columbia relevant to Artemis is not the specific mechanism of failure. Foam strikes and ablative shield cracking are different problems. What makes it relevant is the sequence of decisions that preceded the disaster. NASA knew about the foam strike. It was observed during launch on camera footage. Engineers requested that the Department of Defense use spy satellite imagery to examine the wing for damage while Columbia was still in orbit. That request was denied by NASA management. The rationale was that even if damage was found, nothing could be done about it in orbit. There was no repair capability, there was no rescue shuttle on the pad. So the reasoning went, why look for a problem you cannot fix? The answer, of course, is that knowing about the problem might have changed the decision calculus entirely. Options existed, even if they were difficult. The shuttle could have remained in orbit while an emergency mission was prepared. The crew could have attempted an EVA to inspect and potentially patch the damage. At minimum, knowledge of the damage would have shifted the re-entry from probably fine to maximum risk scenario requiring every contingency. But the decision was made not to look, because looking might have revealed something inconvenient. Something that would require action. Something that would disrupt the schedule. The parallel to Artemis is not exact, but the echo is unmistakable. NASA knows the heat shield has problems. They have looked. They have studied the damage from Artemis I in exhaustive detail. In that sense, they are doing something Columbia's management refused to do. But the decision that followed, to fly with the same shield design and change only the trajectory, carries a similar structural logic. We have identified the problem. We believe we have mitigated it. We are proceeding. And if our mitigation is insufficient, we will find out during the phase of the mission when no intervention is possible. The lesson of Columbia, the one that was drilled into NASA's culture in the years following the disaster, is that heat shield integrity is not just important. It is the single most mission-critical system during re-entry. Everything else, life support, guidance, navigation, communications, all of it is secondary if the thermal protection fails. Because failure of the heat shield is not a degraded performance scenario. It is not a limp home and fix it later situation. It is total, rapid, and unsurvivable. The margin between a working shield and a failed one is measured in seconds and centimeters. And the feedback you get when it fails is not a warning light or an alarm. The feedback is silence. The same silence that mission control experiences during every normal blackout. Columbia's crew almost certainly did not know what was happening to them until the final moments. Telemetry showed increasing temperatures in the left wheel well, but the shuttle's cockpit instruments were not designed to display that data to the crew in real time. By the time the vehicle began to lose control, the structural failure was already catastrophic. There was no time to react. No corrective action was possible. Inside Orion during the Artemis II blackout, the crew will have limited awareness of the heat shield's condition. They will see the plasma glow through the windows. They will feel the G-forces building. They will hear the roar of the atmosphere against the hull, but they will not have a readout that says heat shield integrity, nominal, or heat shield integrity, failing. They will know the outside is hot. They will know they are decelerating, and they will trust that the engineering holds. Come back to where we started. 4 human beings, falling toward Earth, wrapped in plasma, sealed in silence. 122 kilometers of atmosphere between them and the surface. 186 blocks of ablative material between them and 2,000 degrees. 4 minutes between the last moment anyone heard from them and the first moment anyone will hear from them again. And somewhere in those 4 minutes, a question is being answered that determines not just whether these 4 people survive, but whether the species takes its next step outward or turns back. That might sound dramatic. It is not meant to be. It is the structural reality of where we are as a civilization in our relationship with space. We know how to launch rockets. We have known that for 80 years. We know how to reach orbit. We have known that for 65. We know how to get to the moon. We proved that more than half a century ago. What we have not proven, not with modern vehicles, not with current technology, not in the current political and institutional environment, is that we can reliably bring people back from beyond Earth orbit. The Apollo program did it 9 times, 6 of which included lunar landings and then stopped. and for 53 years, we have not done it again. Everything about the future of human exploration depends on re-entry, not on launch, not on transit, not on landing on some distant surface. Re-entry, the moment when you come home, when you convert the vast kinetic energy of orbital velocity into a survivable landing. That conversion happens through the heat shield. It happens through the atmosphere. It happens through physics that we understand theoretically, but struggle to predict practically. This is the part that does not make it into the inspirational speeches or the promotional videos. The challenge of space exploration is not going somewhere. It is coming back. Any vehicle can be aimed at a target and sent on its way. Making it stop safely is the hard part. And for crewed missions, safely is not a relative term. It is binary. The crew either survives or does not. The heat shield either holds or does not. The engineering either works or does not. Artemis II is the first test of that proposition in a generation. The first time a crew has bet their lives on a new heat shield design at lunar return speeds. The first time the Orion capsule has carried humans through the most punishing thermal environment we can intentionally create, and the outcome of that test will reverberate for decades. If it works, we take the next step. We return to the moon. We build infrastructure. We push toward Mars. The conversation shifts from can we to when do we and how far. If it does not work, we stop. We reassess. We redesign, and we lose years, possibly decades, while a generation grows up wondering whether the whole idea of human deep space exploration was a mistake. 4 minutes of silence. No telemetry. No voice. No data. Just plasma and physics and 186 blocks of material doing something that no ground test can perfectly predict. Somewhere in those 4 minutes, the future is being written, and the future of exploration does not depend on how far we go. It depends on whether we can survive coming back.